Hello, everyone. As Johnson mentioned, today I will talk to you about how we can realize efficient and scalable multicast services inside ISP networks. We call our system Yeti because multicast is a beast and we are trying to tame that beast. So first, in the last few years, there has online watching of live events has been gaining a lot of popularity. For example, last December, Amazon Prime live streamed 6 popular soccer games concurrently to millions of their users. The good news on that night that the Reds won the game, but the bad news was actually for network operators. For instance, that network traffic spiked at least up to 70% at multiple regions in the UK and peaked at 25 terabits per second. And this was very big for network operators that actually the British telco CEO mentioned that as demands will grow for such events, then they will have a lot of problems, especially in network planning and capacity. And this is not just an isolated incident. Actually, we have a lot of common services and applications that share the common pattern as well, like Twitch, Facebook Live, and NextVR. And our main idea here, or basically the main network primitive that can be used here is multicast, because it can save bandwidth for ISP networks, because we have a single source and multiple receivers, potentially geographically distributed, and the multicast source only sends traffic independent of the number of the receivers, and all the packet duplication and copying will happen inside the network. Meanwhile, ISP networks also have a lot of routing objectives. For example, traffic engineering. In many cases, for overloaded links, for example, then ISP would like to actually redirect the traffic from one link to another to avoid these overloaded links. In addition, in more recent years, there has been the trend of service chaining, where multicast traffic may need to pass through or traverse a specific order of services before reaching the receivers. For example, here we have a firewall IDS video encoder, so we actually the traffic would go through these services before reaching all the destinations. And since packets may traverse node or link multiple times so that they actually can satisfy the service chaining and traffic engineering requirements, we refer to this new structure as multicast distribution graph. For example, here on the figure, we have node 4, multiple links, node 4 will appear multiple times as the packets will go through it multiple times. So the problem that we are trying to address, or we're addressing in this work, is how we realize multicast distribution graph in the data plane efficiently for ISP networks. And we call this problem generalized multicast forwarding, as it can support traffic engineering, service chaining, and potentially more ISP routing objectives. However, this problem is quite challenging because the first challenge is the state at switches. So if we have only a couple of sessions, that would be okay. However, as we are expecting a lot of, or envisioning more sessions, and maybe in the order of thousands or even hundreds of thousands of sessions, then routers will not be able to catch up or basically maintain all the state. And the problem is not just in the state and the memory. Even if we increase the memory, then the controller, either centralized or decentralized, will need to actually update all the switches when there is a change, which actually put a lot of problems or overhead on these network switches, network routers. In addition, if we try to move to label-based multicast, then most current systems actually result in large label overhead. And this label size or label overhead is fixed and constant across all the links that this packet is traversing. And this consumes network resources such as bandwidth and processing. Finally, also for label-based multicast, To try to reduce the label size, they usually result in ambiguous forwarding. Basically, if a packet arrives at a router, the router may result in false positive. This means that the router does not know where to go next. So mainly they will duplicate the packet on the wrong links, which result in traffic overheads and potentially loops, which are even worse and defy the whole purpose of multicast to begin with. So the proposed solution is Yeti. Again, as I mentioned early on, we called it Yeti because multicast is a beast and we are trying to tame that beast. So it's a new label-based approach to solve the generalized multicast forwarding problem efficiently. Our design is guided by three main principles. So we first move the forwarding state from switches to packets. This makes sure that we achieve scalability at the data plane. However, the main design idea here is that we keep only the needed labels as the packet traverses the network. And this will, as we will show in the evaluation, will reduce the label size significantly. Finally, to make sure that our algorithm is correct, we follow the divide and conquer approach so that we can guarantee correctness. And this is shown analytically in the paper. So to give an overview of Yeti, Yeti consists of two main parts. The first part is the controller, which will be responsible of creating the labels, and the data plane component, which will be responsible on processing these labels in the data plane inside the routers. So the create label algorithm will take the ISP topology and the multicast distribution graph, and then it will create multiple Yeti labels that we are proposing, and then they will be sent to the ingress or to the ingress router for that session. And then at the core routers, as packets are traversing the routers, the router would inspect the labels, then will decide which labels to be removed and which label to stay. And then it will also decide on the output ports where to go next, whether it will be forward, duplicated, or just unicast. Then it will remove all the unneeded labels and keep the needed ones, and so on. To represent all the variations of links of distribution graphs, we actually proposing two definitions here. The first one, what we're calling path segment and branching point. A path segment is a set of nodes that they, without any siblings in the multicast distribution graph, and the branching point is the node that has more than one child. In the paper itself, we actually go deeper here in proposing the label types and how we can encode these two ideas in different label types. So to create the Yeti labels, our algorithm first create a tree from the distribution graph. So given this the graph, we actually transform it to a tree by basically replicating the nodes and links as needed. And this will result in subtrees that will cover all will span the source and receivers, and as well will satisfy all the services that needs to be satisfied inside the network. Sorry. Then the next step, once we have all these subtrees, we will start traversing the tree to encode the labels. So our algorithm has three main steps. The first step is identifying path segments and branching points based on their definitions. Once we identify them, we actually generate the corresponding labels and put them together as expected. And then we optimize the labels as needed. For example, here at router number 8, the left-hand side shows the actual labels without any optimization. But based on the definition of branching point, we don't actually need to create any other labels. So we just reduce the number of labels from 5 to 1, for example, in this scenario. This is also showing an example of how Yeti keeps the needed labels only as the packets traversing the network. For example, here, as we started at router number 1 with 10 labels, as the packet traverses the network, we will end up with less number of labels as we traverse the network, which show that the label overhead will actually reduce or get reduced significantly compared to other label-based approaches. In the paper itself, we have more details on how we process the Yeti labels in the data plane. We also show a proof why our algorithms are correct in the sense that they only forward packets on links belonging to the multicast distribution graph and nothing else. And we also show the time complexity of our control plane algorithm, which is very important to show that our algorithm can run on commodity servers. We evaluated our system in two setups, in large-scale simulations and in a test bed. For simulations, we used 14 real ISP topologies ranging or has different sizes, and we simulated the dynamic and diverse 1 million sessions over an extended period of time. And we compare our work against the closest approaches, basically the stateless one, which is label-based approach called BIER-TE. This is still like it's an internet draft, and the stateful approach like OpenFlow or IP multicast, we just call them stateful approaches and hybrid approaches where these systems can use labels and state at the same time. We also show an intensive or extensive analysis of Yeti labels and how they actually save more labels, and most or all of these results are actually in the paper. So first, we start by comparing Yeti versus BIER-TE in terms of label overhead. So we are interested in plotting the label size versus the number of hops from the source of the multicast tree or distribution graph. And we find that BIER-TE uses fixed label sizes in this largest topology of our data set up to 110 bytes. And our system, Yeti, although it uses around 150 and for the first hop, it actually reduces very quickly, maybe after just 1 or 2 hops compared to BIER-TE. And this is because Yeti keeps only the needed labels as the packet traverses the network. To get an end-to-end understanding of the label overhead, we define the label overhead as the label size multiplied by the number of hops that the packet traverses. And this is basically, in this figure, is just the area under the curves. So we find that BIER-TE actually result in large overhead compared to Yeti, this small blue thing. And on average, across all the ISP topologies, Yeti reduces the label overhead by 65% on average. In terms of scalability, we compare Yeti versus the stateful and hybrid approaches, also still in the simulation. So first, we plot the number of, or the state, which is the number of routers that need to maintain state in the session versus the receiver density of that session. And we find that the OpenFlow and stateful protocols in general will not scale very well, as they will require a lot of state or a lot of routers to maintain state in the network. LIPSIN, on the other hand side, although it reduces the state compared to OpenFlow, but this is actually still relatively large. So for example, in this instance, this is around 20% of the router in the session that need to maintain state. And at the same time, Yeti does not need to maintain any state at any of core routers at all. Again, the problem of the state is not just the memory, but actually the rate of change. So for example, a single change in a multicast session, which again could be very common in current live watching of videos, is that for OpenFlow, it will need to update 48 core routers per session. LIPSIN will need to update 9 core routers, while Yeti will need only to update 1 ingress router. So in general, Yeti scales well and can handle dynamic session better than the other approaches. We also evaluated Yeti in a testbed. We have 2 implementations actually. The first one is in NetFPGA using Verilog, and we showed in the paper how we can implement this in P4. And we basically focused on the situation where we are stressing Yeti by sending all the packets that require copying and rearranging of the packets so that we can stress the router. We here plot the packet rate versus the packet size, and this is the number of transmitted packets from the server, and these are the number of processed packets by the router. And this is also the throughput showing that it can sustain the high rate efficiently or very good. And also we want to make a note that this is where most common multicast applications will work, using relatively large packet sizes. In summary, Yeti is a fully stateless label-based approach to solve the generalized multicast forwarding problem. Yeti is the only system that, at least that we are aware of, that is scalable, proven to be correct, and can support most current ISP routing objectives while reducing the label overhead significantly. Thank you.